So welcome back to the second of our Oxford Discrete Maths and Probability seminars. It's a huge pleasure to have Marcus Michelen here, and he's going to talk to us about separation of roots of random polynomials. Over to you.
Hey, thanks so much for the introduction and the invitation, and thanks everyone for coming here in this afternoon or morning, wherever it is you are. I'm going to talk about some joint work with Oren Yakir, who's currently a postdoc at MIT, and I'm taking the perspective that maybe the majority of you haven't seen too much about random polynomials before, so I want to give a very gentle introduction to random polynomials in general, how extremal combinatorics and Fourier analysis comes in, and then tell you about some of the work that we did. Also, please do interrupt me with questions. I love being asked questions. So, what is it that we're going to be talking about? We're going to be talking about polynomials of degree n, where the coefficients are independent and identically distributed. You should think about them as uniform from -1 and 1. So typically discrete is going to be the types of coefficients we want here. You can also think about them as Gaussians, or more generally just mean zero variance one, and we can talk about some more technical assumptions later on. So this polynomial is degree n, so it has n roots in the complex numbers, counting by multiplicity. Some of them might be real, because my coefficients here are real, but in general, I'm going to be thinking about these n roots in the complex numbers. And the guiding question is, what can we say about them? There's a lot of behavior that you could ask about when you have a polynomial like this, and I want to just take about 3 seconds for you to imagine what it might look like if you generate the roots of a degree 100 polynomial. And I imagine many of you have seen a picture like this before, but they end up looking like that. Where the circle here is the unit circle, and the blue points are the roots. So on the next slide, I'm going to unpack a lot of different properties of this picture, and it'll be slightly larger. Um, but I just want us to kind of stare at this image for a little while. So this black circle is the unit circle in the complex plane, and these 100 little blue dots are the roots. So what do we see from this? Maybe the first obvious thing that we see is that most roots, but not all of the roots, are close to the unit circle. In particular, I have some stragglers going on here. I have a few farther out and a few on the inside. And I want to point out that that actually is not an artifact of n only being 100. That's a genuine property of what's going to happen here. We'll end up seeing a theorem that will tell us that the majority of the roots are close to the unit circle, and we'll even talk about how close they end up getting to the unit circle. I also want to point out that we have that they're approximately like equidistributed rotationally. If you draw any little sector from the origin, it's going to have sort of the correct proportion of the number of roots there. So there are at least two other properties I want to point out here, which is my coefficients were real. So I have this nice symmetry, right? If I do complex conjugation, so the upper half plane and the lower half plane give me the same thing. And in fact, I also have some real roots. Here I think I have two real roots, if you look carefully. The last thing I want to point out, which is maybe the least obvious of the three things, is that we have some notion of repulsion between the roots. The roots aren't exactly going to be spread out the same way if I had just spread them out around this general unit circle thing randomly. There you would see a little bit of clumping and you'd see bigger gaps. Here we're seeing that they're going to be repelling each other a little bit, and that's giving them this more uniform spread. So I want to pause here and ask if anyone has any questions or notices any other properties about this that they want to find interesting. This is the end of my list of things I was going to say about this image. Okay. I want to note one thing, which I didn't want to put on the slide because it's not necessarily as key. We're going to see that this behavior doesn't depend very much at all on the coefficients. The thing that will depend on the coefficients are these stragglers on the outside. For instance, with my coefficients being 1 and -1 only, I'll never have a root with absolute value less than a half or bigger than 2. But if my coefficients were uniform between -1 and 1, or if they were Gaussian, then I would have those with positive probability. So you should think about what's going on near the unit circle as universal, and stuff further away really depends on what's going on with the coefficients. Okay. So what is our plan for today? So first, I want to tell you about some classical theorems that tell us what these properties were about this picture. I then want to isolate a single tool that's actually used for all three of those properties, which is Erdős' solution to the Littlewood-Alford problem. And I'm also, maybe a little ambitiously, going to outline two proofs of it. Each is going to be one slide only, One will use extremal combinatorics ideas, and one will be Fourier analysis ideas. Sort of just to give you an idea of how you could go in either direction to tackle these kinds of problems. Then I'm going to tell you about our results and how we proved them. And I also didn't add the question of why we proved them, but I can also discuss why we proved them. Perhaps that's also relevant. And then maybe a little bit about open problems in some future directions. Okay, so I'll again take a quick pause as we look over our plan for the next 45 minutes or so. Okay, so I'm going to talk about the results sort of historically rather than in the order I presented them. And the most classical results about random polynomials were about the number of real roots. So there were predecessors by Bloch and Polya and Littlewood and Offord, but the first sharp result was Katz in 1943 said when the coefficients are Gaussian, the number of real roots is around 2 over pi plus little o1 log n. This is true in expectation and also with high probability. So I have n roots, but only log n of them are real. So it's actually a very small fraction of them, but a growing number of them. There's also a very interesting historical artifact where in this paper, he wrote the sentence that in the case the coefficients are not normally distributed, but all have the same standard deviation, one can still prove this result. And he was very honest in that 3 years later, he extended it to uniform between -1 and 1. And he was like, I don't know if that's really true. Upon a closer examination, it turns out that the proof which I had in mind is inapplicable to the discrete case. So I think this is a very interesting artifact, like sort of historically, and we'll see what it is about Gaussian later on that's quite useful. But we now do know this in generality for +1 and -1. Erdos and Offord proved it. For +1 and -1, I didn't explicitly state what random variables their proof works for, but we now know it even just under mean 0 and variance 1. Okay, so again, I'll pause one more time for any other questions about number of real roots. I also want to add, we actually know quite a bit more. We also know, I believe it's by Ibragimov and Maslova, that we have a central limit theorem even for the number of roots. And the variance is on the same order as this. You should think about it as roughly Poisson of 2 over pi log n. So this is a universality phenomenon, in that the behavior doesn't really depend too much on the actual distribution of coefficients. As long as we have, let's say, mean 0 and variance 1, which is what we need for the central limit theorem to hold, then we're going to end up having a theorem like this holding. Okay. So I want to talk now about bulk behavior. So most of the roots are near the unit circle. So I'm going to let this script z denote the 0 multiset of roots. Now for each epsilon, it'll turn out the proportion within epsilon of the unit circle tends to 1. It also turns out that the number in a given cone is the correct amount. And of course, here you need b and a to not be, stupidly chosen so it wraps around too much, but it's going to give you the correct percentage. What's also really interesting about this is that this theorem has almost no probabilistic content. It's true deterministically, provided the coefficients are on the same exponential scale. So Erdos-Turan proved that these two properties hold as long as I have no coefficient is exponentially bigger or smaller than the top and bottom coefficient. I also want to add that they proved a very quantitative version. So the number in a sector is going to be the correct amount plus something on the order of root n in the case of the random polynomial we talked about. Okay, I'm going to give a very quick hint of how one might prove this as well. So this is the same as actually saying that the probability measure, where I put a little point mass on each root, converges to the uniform distribution on the circle. Okay, so the way you prove this, and I put this in red because it's sort of poking at something much more technical than I want to talk about here, is it's enough to prove 1 over n log modulus of the polynomial converges to 0 for all z in the unit disk and log z for all z outside of it. And the reason for that, if you accept a sketchy equality, is that you can write this probability measure as 1 over 2 pi times Laplacian. Oh, I should have a 1 over n there as well. But this is an equality in distributions, and thus it's enough to show that log f is going to converge when rescaled to sort of the analog of log f for this measure here, which turns out to be exactly 0 in the unit disk and log z outside of it. So it's a very quick sketch of how you prove it, if you believe epsilon complex analysis. Now, we can also talk more quantitatively of how far away are most of the roots, and most of the roots are big theta of 1 over n away from the unit circle. And here we really mean big theta, so if I look within a small constant over n, I'm going to get only 1% of my roots are there, and if I make it 10 billion, I'm going to get 99% for, sufficiently good 1% and 99%. So this was proven in a line of work by Shep and Vanderby for Gaussian coefficients, Ibragimov-Zitouni for more general coefficients, and Konyagan and Schlag proved some other properties related to this problem. So this is what's already telling us the majority of the picture. And I want to again recap and say that this is only telling us something about what most roots are doing. This is saying something about the average behavior of a random root, you could say. And now something a little bit more tricky to actually quantify is what it means to say the roots repel each other. So most roots are within 1 over n away from the unit circle, and there are n roots. So that roughly means if I look at like a little ball of radius t over n, I should have on the order of 1 root there. Right? This is just because I can look at the area of the annulus, which is 1 over n, and I have n roots, and the area of this little ball is 1 over n squared. So that's just saying, just looking at area counts. This should be the truth. And now, what might it mean for roots to repel each other? Might say something to the effect of, if I have one root in a ball, it should be less likely to have another. So in fact, this is something that can be proven. If I look at a ball of radius t over n, then in fact, near the unit circle, at least 2 roots falling in there is going to be much smaller than at least 1 root squared. But here the key technical question, which will be a recurring theme later on, is for which t is this true? So it turns out you can always take t to be some small polynomial, and it's true as long as its probability is little o1, which happens when t is little o1. And it's unclear exactly who to originally credit this to, but various works of Schiffman and Zeldich proved this phenomenon for Gaussians, and works of Tao and Vu proved it's universal. So this exact form will be relevant for us later on, that's why I kind of wanted to highlight it here. So okay, we've now seen 3 properties of random polynomials. We saw that the majority of the roots are going to be near the unit circle, and they're going to be spread out roughly evenly. We saw that they're also going to be on the order of 1 over n away. We counted the number of real roots, which isn't too many, and we saw that the roots repel each other. I'll pause once more and ask if there are any questions before we go into the second section.
Thanks. On the real roots, you said it was approximately Poisson distributed, and so if we condition on having at least some number of roots, do we get like that sort of Poisson behavior of the more than just the point distribution of Poisson, but the property that if we condition on at least this many, then it's still Poisson.
Yeah, so that will turn out to not totally be true. So I think you should sort of just think about it as approximately Poisson. It'll turn out also that the probability there are no real roots will not be e to the negative this number, but it will be approximately that with some other number. So one way to think about it is on one scale, it's sort of Poisson, which is telling us just that it's Gaussian because the mean is growing. And that's kind of one way you can think about it. If I look at yeah, so maybe another thing to say is if I look at a window in which I expect there to be only constantly many, it turns out that you won't necessarily have that it's Poisson because you have this repulsive behavior. So in particular, this is getting a little further in the weeds, but if I zoom in at a point, let's say 1, and I look at what the roots look like near there, it's not going to end up being a Poisson process because I have repulsion of the roots.
Okay, so that's happening on a smaller scale, and then once I get to a big enough scale, then it's Poisson.
Well, it looks Poisson sort of in the sense that this is approximately Gaussian. I don't think you're going to be able to prove a very strong total variation bound, for instance.
Okay.
Not anything much further than what you would get for like a central limit theorem. Yeah.
Thanks.
Yeah, absolutely. Okay. So we saw our three properties, and each section that I'm talking about is going to be approximately independent. So if you've already fallen asleep, this is a good time to wake up because this is a self-contained section. So relevant for all of the pieces we talked about is understanding the probability that our random polynomial is small. So it's at least, I think, relatively clear that this is the case for counting real roots and also the case for counting, for quantifying repulsion. I also wanted to add that in order to show this uniform distribution or convergence to the unit circle, we had to understand log of f. And the issue there is exactly at 0. It's not so bad to show f isn't too big, but showing it's too small is harder. So truly, the Littlewood-Offord problem is the most relevant bit for all three of the pieces that I discussed. So let's take a look at some fixed z, where z is going to be basically 1, and I'm going to look at the probability it's less than 1. So I want to first understand why that's the correct thing to think about. So I want to note that if I look at, let's say, the variance of it, which is just the expectation squared, I get something like n. So typically, I should expect f to be like square root of n. So the probability it's less than 1 really is the probability it's much smaller than it's supposed to be. So I can write out what f looks like. And when we think about it as a polynomial, it's these xi's multiplying by z. But I can also just think about it as some numbers multiplying by these random variables and adding them all up. So more generally, let's look at this random linear combination here, where I'm going to assume my coefficients are, let's say, at least 1. So how big can the probability that it's less than 1 be? What's the worst possible case? And if I make the all ones case and I have n equal to an even number, then I end up getting that it's exactly this middle binomial coefficient times n, 2 to the negative n. And then if you like Stirling's formula, you can get exactly what the constant is here, but it's n to the negative a half for some constant. And the Littlewood-Offord problem was understanding if this is the worst case. And Erdős' solution, which we'll see even a proof of, is that this is indeed the case. And we'll actually even see for the case of plus minus 1 coefficients, you can get literally this exact bound with the middle binomial coefficient. So you can get the correct constant as well. We're going to see two proofs that are totally orthogonal to each other. One is extremal combinatorics, which is Erdős' original proof, and the other is a Fourier analytic proof. I also want to mention that Littlewood and Offord originally proved this with a polylog loss, and this was in trying to understand the number of real roots of a random polynomial. So this was exactly the Littlewood-Offord paper I referenced earlier. So I know we have people from combinatorics and probability here, so first we have a combinatorics proof, and then we'll have the probability proof. So let's deal with real coefficients. Let's have all my coefficients being at least 1, and let's look at the random linear combination. Then, in fact, we're going to show that the middle binomial coefficient is the worst case. So the first thing I'm going to do is I'm just going to assume my coefficients are at least 1. Right? Because these xi's are symmetric, I can just replace aj with negative aj, and I'll have this holding. And now I can associate to an instance of plus 1 and minus 1s this set of plus 1s. Now, if I think about S like this, I can think about X as just a function of the set S. So now I'm going to look at what's the structure of the set S that's giving me that this is less than 1. If you give me some subset that's a strict subset of another one, then they have to differ by at least 2, because I'm flipping at least one coefficient, and that plus is going to switch from a minus to a plus, and I'm going to get this 2 value. So in particular, if I have that xs is less than 1 in absolute value, and t is something either contained inside of it or bigger than it, then I have x of t is actually bigger than 1. In extremal combinatorics, this is called an antichain of the hypercube, and a theorem you learn in a first extremal combinatorics class tells you that the biggest one of these is exactly the middle layer. So sort of amazingly, actually, one of the easiest proofs of Sperner's lemma is to prove this with probability, but you can also think about it as taking some antichain of the hypercube, and you can just compress it down to the middle layer, is another way to think about it. So this is an extraordinarily sharp result, or I also think I put a little square, because that's the end of the proof. You just have to divide by the total number of sets. This is a very sharp result. It gives you the correct constant. I also want to note that if I look at quadratic polynomials, so now I'm looking at, let's say, a multi-affine one of degree 2, then this proof no longer works at all. There are a few reasons, and one key reason I just want to add is that you can't all of a sudden assume the coefficients are positive. So you all of a sudden have a more complicated system when I do this in more than one degree. Just something to add. You can also make this sort of a thing work for other random variables, but it's a little bit trickier, and you won't get the correct constant. So I'll pause and ask if anyone has any questions on this before we see a very quick and dirty Fourier proof. Okay. So I'm going to show you a weaker version, sort of rapid fire with Fourier analysis, just to give you a quick impression of what's happening. This will be the only slide in which we have any Fourier analysis. So we're going to deal with the same thing. I'm going to assume my coefficients are bounded. And this proof is also actually going to work for arbitrary non-degenerate random variables, as long as they're just not some explicit constant. And I'll highlight exactly where it is that we could make use of that. Then you get C over root n, where that C is going to depend on the distribution of the coefficients. So let's take a quick detour to Fourier land. I can look at the probability as just the expected value of the indicator evaluated at x. So what I want to do is find some nice bump function to approximate this by. So g corresponds Fourier transform-wise with sine theta over theta. So if I convolve g with itself, its Fourier transform is sine theta over theta squared. Let's note that g star g has compact support. And I can note that g is at most sine x over x squared times some constant. And I'm not going to care at all about constants here. So what's the quick chain of inequalities for how you can prove something like this? When it first just bound g above by sine x over x squared, that's just a pointwise bound. Now I can just take the Fourier transform of each side, and I get the Fourier transform of sine x over x squared is g star g, and the Fourier transform of x is the expected value of e to the I theta x. But now I can just remember that g star g is supported between -2 and 2, so just use a triangle inequality. It's just bounded by some number. And now what's the Fourier transform there? It's just a product of a whole bunch of cosines. And now the idea is if you give me some theta, what you end up having is for the vast majority of theta, a whole bunch of these cosines are going to be less than, let's say, 0.99. So that means in particular, maybe not literally pointwise, but if I shrink -2 to 2 to be smaller, I will actually have this pointwise. You'll get some bound like this, approximate like a Gaussian. And that's just 1 over root n. So this is very quick and dirty. But I just want to indicate the way that you do this is you just approximate by some nice bump function whose Fourier transform has compact support. And I'm looking at a product of a bunch of cosines, which is witnessing this cancellation. This red inequality, I also want to point out, is something you can prove for most theta, provided psi is just arbitrary non-degenerate. Okay, so now we've seen this main tool of the Littlewood-Offred problem. It's telling us if I add up n independent things of the same size, the probability it's small is like 1 over root n. I'll pause once more for questions before we move to our next section. Okay. So let's return to our random polynomial. We're done with the Littlewood-Offred tool, but it will come back. So we're now looking at Fn, which is the sum, it's the degree n, independent coefficients, let's say plus minus 1. I'm going to look at the multiset of zeros. Recall most roots are near the unit circle, and the roots experience repulsion. So if I want to capture the repulsion, one thing I can do is try to understand the smallest distance between an adjacent pair of roots. So let's take a look at the minimal separation of roots of Fn. And I want to note the way that I wrote this, if I did have a double root, then this minimum separation would be 0. So first we proved that Mn is on the order of n to the -5/4 with high probability. And in particular, we proved that we have a limit law for what happens when you rescale. So it converges to e to the -c lambda to the 4th, I'm sure if you're teaching some statistics class, you might know the name of this random variable, which I never remember the name of it. It's a 4-3-different exponential random variable. I also want to note that this C doesn't depend on the distribution of coefficients, and we prove this for mean 0, variance 1, and a good enough tail bound. So before I take questions, I want to note that there are a few things here to note, which is there's the 5/4, which we owe an explanation for, and there's also the power of 4. And actually, both of them are going to represent repulsion between roots in some way, and that's what I'm going to argue on the next slide. Before we understand what these numbers are sort of meaning and how they're reflecting repulsion, I'll pause again and ask if there are any questions about this. Okay, lovely. I also want to add, I didn't want to write it on the slide here. If I look at the collection of distances rescaled by n to the negative 5/4, we get a Poisson process that's inhomogeneous. And that's just an artifact of the proof. It just comes out right away. Okay, so why is it that these are capturing repulsion? So I want to give a toy example of what would happen if I pretended there was no repulsion. So this is our theorem. We said if I look at the number of how many roots there are within distance lambda n to the negative 5/4 of each other, I'm going to rescale to this quantity here. So let's pretend I'm dealing with a model that does not have any repulsion. So I can think about saying, let's place n points of distance 1 over n from the unit circle, right? Just in this little thin annulus. We can compute what the separation is like there. So what we're going to end up seeing is that we're going to prove our main theorem by proving that we have convergence to a Poisson for Poisson of mean c lambda to the 4th. So we're going to try to do something like that here. I want to capture the number of pairs that are within a certain distance, and then I'm going to tune that distance until it's order 1. So I'm going to let epsilon be small and compute the expected number of pairs less than epsilon. There are a whole bunch of ways you can do this for this toy problem. I'm going to do it in a way that'll translate nicely to what we want to do for roots. So for a given z, the expected number of pairs in the ball of radius epsilon about z is, well, first I just have to sum over all n squared pairs. Then I have to look at the probability 2 given points lie in here. But that's just independent, so the probability 1 point lies in there squared. And then I can compute that by looking at the ratio of the ball to the annulus. And I'm going to end up with n to the 4th epsilon to the 4th as this probability, the expected number of pairs. Now, in order to understand the expected number total in the annulus, I need to understand how many of these balls it takes to cover the annulus. It takes around 1 over n epsilon to the negative 2 balls to cover it. That's just, again, considering only the area of the annulus and the area of the ball. So the expected number of pairs with distance less than epsilon is n cubed epsilon squared. So this is telling us if I have n squared epsilon squared is big O of 1, so in particular, if I have epsilon as n to the negative 3/2, then I'll end up hoping, likely, the number of pairs at distance epsilon is Poisson of mean n cubed epsilon squared. So if you're a bit more careful, this will prove this sort of a limit here. So we can see, in a sense, the power of 2 on the exponent for lambda is corresponding to the fact that we're in 2 dimensions. It's coming from the epsilon squared in the area of the ball. And as we saw, we ended up getting, for random polynomials, n to the negative 5/4 lambda to the 4th. So we're going to end up seeing that each of these two is going to come from a slightly different aspect of this. I'll pause again and ask if anyone has any questions.
So in this approximation, epsilon's chosen after n. Is it?
Yes, epsilon is going to be a function of n. Epsilon is going to end up being like n to the negative 3/2. Yeah.
Right. Okay. Yeah. Gotcha. Cheers.
Yeah, absolutely. Other questions?
Yeah, I mean, do you have a rate of convergence?
Okay, so for this you definitely could, right? So for this you certainly could do such a rate. For random polynomials, we don't have a rate explicitly. We also Yeah, it's a great question. Easy answer is we don't have a rate. I'm not sure what could be mined from our proof, but the easy answer is we don't have a rate for the random polynomial one.
Okay, thanks.
Mhm. Okay. So how is the actual calculation different? As we just saw in the previous slide, for independent points, we really used the fact that you have two points in a ball is the same as 1 point squared. And I just told you on a whole other slide before that we know that that's not true for roots. So we'll end up seeing for z near the unit circle, the expected number of pairs that lie in there is going to be on the order of n to the fifth epsilon to the sixth. And when I write this as a board talk, I write this as big theta of a theorem because you can make it an authentic theorem, but I haven't told you enough to make it a rigorous theorem here. Sorry. Sergei Pirogov is asking if there's repulsion for independent points. There's not repulsion for independent points. You end up getting that if I have condition on a single point being in there, probably there's another one being in there is approximately the same as n gets very, very large. There's only repulsion in the sense that I only have n points, but other than that, there's no repulsion for points, is what Sergei Pirogov asked in the chat. Okay, so going back to this, we do have repulsion for the roots here, in that the behavior of having 2 points in here is different, but it's not totally clear for what epsilon right off the bat something like this is true for. And this is where it becomes a bit more technical. We saw this is always true as long as I'm just a little bit less than 1 over n, and polynomially less for a small polynomial, but we actually need something a little bit better than that. So I want to note that you can't have something like this holding for all epsilon. Because if I have that n is, let's say, divisible by 4, then I can have that 1 is a root of f and its derivative at the same time, with probability 1 over n squared. So of course, if I make epsilon very small, n to the fifth epsilon to the sixth is much less than 1 over n squared. So the value I'm going to be able to take epsilon for can't be arbitrarily small. At least not for all z. So it turns out the problem with z equals 1 is that the argument of it, which is 0, is close to a rational number of small denominator. Right? I can write it as 0 over 1. So if I want to get a better epsilon, I could actually look at z equals I and take epsilon polynomially smaller than I could for 1, because the denominator there is actually a little bit bigger. And I can take it even smaller, right, if I look at e to the I pi over 4. So it'll turn out, if I want this to hold for an arbitrarily small polynomial power, I can just omit points that are close to some root of unity of given order. I also want to note, I said actually root of unity, but I mean that the angle corresponds to a big O of 1 root of unity. So this isn't a new phenomenon. This is what people like to call inverse Littlewood-Offord theory. It's saying that if I don't have very nice control on this for small epsilon, on the probability it's less than epsilon, then that means there must be some structure holding. And here the structure is just going to be that e to the I theta is close to a root of unity. Okay. So with this perspective here, I want to go through a quick outline of what it is we actually did to prove this. And we're going to come back to the outline as well. So we proved that we have the probability it's bigger than lambda n to the negative 5/4 is going to converge to e to the negative c lambda to the fourth. So we're going to sketch how we can prove this, where what I'm going to really show is that if I let y lambda be the number of pairs at distance lambda n to the negative 5/4, then it's going to converge to a Poisson random variable of the correct mean. So we're going to use the method of moments to show this. And in particular, we're really doing this for each fixed k, and thus, to answer Emmanuel's question again, we're not going to get a very good rate of convergence from this. There's nothing explicitly written down. So just to recall, in order to show convergence to Poisson, I have to show these lower factorial moments converge to mu to the k. It's a bit like saying if I sum over all k tuples, the probability that they have this is going to be approximately the mean to the k. So the first thing we have to do is we have to omit pairs that are quite far from the unit circle. Polylog over n far enough is going to be enough. And if we have time, which I think we will, I'll be able to say at least a couple of sentences about how we do this. Then we have to omit pairs where z is close to a root of unity, where it just is bounding those of a given denominator. This we can handle with a Littlewood-Offord type result. We don't need exact sharp control over epsilon in the previous one to handle these. The idea is that there aren't that many roots of unity. There aren't that many points close to it. And now here's really where the work is happening, right? So if you give me k points that are separated far enough away, the probability I have pairs within distance lambda n to the -5/4 is going to approximately factor. That's going to be exactly this power of mu to the k once I sum over all these separated k tuples. So this is done by comparing to a Gaussian, and we'll see more about this on the next slide. And the proof is just a stronger version of the Fourier proof of the Littlewood-Offord result, but we now have to work quite a bit harder to bound the Fourier transform rather than just bounding cosine to the n. So my plan for the rest of this proof is I'm going to say one slide about this last bit, one slide on roots far away from the unit circle, and then I think we're just at open problems. So I'll pause here and ask if anyone has any questions. Okay. So I want to indicate how can we detect when there's a root near a point, and then how can I detect that there's a pair? So first, let's say I take some point that's deterministic near the unit circle. How can I tell if I have a root near there? Well, I can just Taylor expand, and I'm just going to pretend the error is small enough, which it will be if w minus z is small. And the idea is that if f over f prime is atypically small, and I don't have anything weird going on with the second derivative, then I should have a 0 approximately at z minus f over f prime. Right? This is just from solving this, pretending my error term isn't going to contribute, which is okay as long as f double prime is not crazy. Now, to see where two roots are, I'm going to need some event depending on f, f prime, and f double prime. Right? Because I can only see one root with a linear approximation. To get two roots, I need some kind of quadratic approximation. So, to calculate probabilities related to f, f prime, f double prime, we do a Gaussian comparison or local central limit theorem that's going to have stronger and stronger epsilon as the further z gets from roots of unity with small denominator. So this is exactly the point I was talking about on the previous slide of saying that in order to, maybe it was 2 slides ago now, in order to handle this repulsion, we can only figure out exactly how this behaves for an epsilon that's polynomially small, depending on how nice the point z is. So we have to treat the different points differently, and for points that are pretty generic, we can prove this for an arbitrary polynomial power. Okay, so there's actually something kind of implicit here that I want to spend one more slide on, which is if I take a look at this Taylor expansion, if f prime is large, there's more likely to be a root near z. Right? Just because if f prime is large, f over f prime is going to be fairly small. So we'll actually see that this is why repulsion happens. So I told you that repulsion occurs, but I didn't sketch for you why it happens or explain it. And I'm going to have just one slide explaining why for random polynomials and random functions more generally, the roots tend to repel each other. So we saw if there's a root near z, there is going to be a root near z if f over f prime is small. So if f prime is large, there's more likely to be a root there. So if I take a typical root, f prime does not want to be small. Now, there's another way you could think about this, which is like imagine you're watching a bunch of people running on a circular track, and 5 are really fast and 5 are slow. Who are you going to see more often? Right? You're going to see the fast runners far more often than the slow runners. And here in this analogy, you're the origin, and f prime is, how fast they're going. So you're going to see the things crossing the origin more often if they're moving a lot faster. So this means at a root, typically f prime is not small. But why does this imply we have repulsion? Well, if I have two roots that are close together, the mean value theorem or Rolle's theorem will say that f prime is 0 somewhere in between them. But if those are close, that means the derivative is small. So now we have a tension. If I have two roots that are close together, the derivative is small, but on roots, the derivative typically doesn't want to be small. So exactly this is telling you that roots typically repel each other. So if you go through this sort of an argument, you can understand the distribution of the derivative sort of conditioned on there being a root at 0. You can look at the derivative conditioned on there being a root. I also want to add that in the case of the coefficients being Gaussian, you can literally compute that exactly, and that's what Katz did. So everything there is nice and Gaussian. If I condition on a vector of a Gaussian having one coordinate being something, the other part's still Gaussian, and that's why it's so nice. Okay, so this is an explanation of why roots repel each other. And the same story holds for a lot of random functions. In fact, this is another reason why eigenvalues of random matrices repel each other, if you've seen that picture. Okay. So the one last wrinkle I want to mention is I want to eliminate roots that are uniformly far from the unit circle. Right, so I told you that the behavior of f is not universal on z far from 1. And I can take a look at what happens for z in the unit disk. And I can consider the n equals infinity limit of this random power series. As long as the x's are well behaved, this is going to be analytic in the unit disk. So I want to note something that's not necessarily immediate if you've never thought about it. But this is not like a Gaussian. And in particular, this is not a continuous random variable. We have some local experts on this problem on the Zoom chat as well. But a theorem of Erdos states that, in fact, you don't even have a continuous random variable if I plug in 1 over the golden ratio. So you can't use Gaussian comparison here because it's not going to be close to a Gaussian. So we needed a separate approach, and we proved a separate theorem by totally other means, just saying as long as this random function is analytic, which happens when it has a log moment, then almost surely it has no double roots except maybe at the origin. So of course it can have a double root at the origin if the probability it's 0 is positive, because I could have, xc0 and xc1 being 0. Other than that, it won't have a double root almost surely. So this is a separate perturbative proof where you take the first m coefficients, and it's unlikely that the rest of the polynomial will combine to give you a double root. And that's exactly using the solution to the Littlewood-Alford problem in this very generic sense. Okay, so with these last bits all in place, I want to recap the strategy we had, and then we're going to move on to open problems. So this is what we proved, and we proved it by proving convergence to a Poisson random variable, the number of pairs less than a constant over n to the 5/4. We did method of moments, so we needed to sum over all k tuples and look at the probability I have that these are approximate close roots. I omit pairs by a perturbative argument, looking at an infinite power series corresponding to n equals infinity. And I can bring this sort of back by a compactness type of argument. I can omit pairs where z is close to a root of unity via a Littlewood-Alford approach. And then we do a Gaussian comparison to understand what's happening for f, f prime, and f double prime at a bunch of points that are separated. So I need to understand if I look at k points far apart, the probability I have double roots is basically some function of the first two derivatives there, and then we do a Gaussian comparison to do it. Okay, that's all I'm going to say about the proof, so I'll pause here once more for questions. Okay, so one natural open question, which I've sort of been avoiding exactly what we do, but we proved our theorem for sub-Gaussian random variables, right? Meaning that the tail behaves no worse than a Gaussian. I think if you really hated yourself, you could rewrite our proof with only finitely many moments, but finitely many is probably like 100. Um, a corollary of it is the probability it has a double root other than at 0 is little o of 1. And we'll see on the next slide that actually this is the theorem we wanted, like for another result. And this was not written in the literature, except in the case of very nice integer coefficients here. So for plus minus 1, this was known by sort of algebraic methods by Pellet, Sen, and Zeytouni, and also by Feldheim and Sen. And they proved something quite a bit more than this. They proved a lot of rich behavior here. But like this should just be true, right? We shouldn't need any tailbound in order for this to be true. And I suspect if you give me any non-constant random variable and look at this power series, then that probably has a double root other than at 0 should be little o1. And everything I talked about for our approach was quite analytic. We're really dealing with how big everything is, and that's just not true if I don't make any further assumptions here. So it seems like something perturbative and maybe a little bit of algebra would be useful. Our proof is like completely analytic. There's like no algebraic information at all. We're just figuring out how big everything is. So I think this is a nice open problem, which it's kind of crazy this hasn't been proven. So I want to maybe just give a little reference to the question we were originally considering, which is we were studying the discriminant of a random polynomial. And the discriminant, you can think about it as the leading coefficient to the 2n. Oh, that should be 2n minus 2, not 2n minus n, of course, times a sort of van der Waals determinant of the roots. Now, you can also think that this is really capturing the repulsion in a sense, right? If it's 0, I have roots that are close together, and it's really telling me about sort of how average close or far roots are. And the theorem we proved, which I don't want to really harp on too much, is we proved just that if I take log and I subtract out 2n log n and divide by n, I get convergence. So I get a law of large numbers for log of the discriminant. It means you sort of predictably have this behavior. And when we tried to prove this theorem, we realized that you have to have really good control over repulsion of roots on this scale. I have to truncate log at 0. And that was how this problem came to be. So we were interested in studying the log of the discriminant in part to analyze questions related to irreducibility of random polynomials. This is nothing about irreducibility of random polynomials, but I want to highlight a really beautiful conjecture. I credit this to Barry Soker and Cosma, although it maybe existed earlier, but we suspect if you give me a random polynomial, with high probability the discriminant will not be a perfect square. This is again something Emmanuel knows quite a bit about, but why this comes up is that the discriminant's a perfect square if and only if the Galois group is a subgroup of the alternating group. So you should think the discriminant is some just huge integer. It's like n to the 2n. Probably the probability it's a perfect square from this analytic point of view is quite small. Something a little bit tricky, just for that heuristic, if you're thinking a bit like a probabilist, you might say, well, the probability it hits any given point might be n to the negative n or something like that. So you take the square root of how big it is. But I only have n bits of randomness, so that can't actually be true. So just to state, this is a huge integer, and it's not going to be anti-concentrated enough in order to just omit perfect squares like that. You'd have to do something a bit more algebraic if you want to prove this. So to recap today, we looked at the random polynomial with independent coefficients. I told you classical work of Erdos-Turan and others to show most roots are near this unit circle. The roots experience repulsion. We handled how far apart the minimal separation of roots is. We did this via the method of moments. And that's all I have today. So thank you.
Thank you very much, Marcus, for a beautiful talk. Any questions? Any questions from anyone in the room or elsewhere?
Sorry, you claim that if you take n independent points in the strip around the circle, then the probability that the minimal distance is about n in the power minus 3 to 2,
Yes.
3r, yeah? So it is a repulsion, or what is it?
No, it's not repulsion because it's asking about the minimum of a whole bunch of dependent stuff. So the typical size is going to be 1 over n. But if I look at the minimum possible separation, it'll be like that.
Yes, but it's better estimates than for roots of the polynomial, yeah?
It's smaller than for roots of a polynomial.
Aha. Oh, yes. Thank you.
I've made that mistake too. Yeah.
Any further questions? What happens if you lose the finite variance condition?
Yeah, great question. So I would suspect that for this problem, it's not totally obvious to me what you would have, because you're not comparing to a Gaussian anymore. It's plausible if you work quite hard. Okay, I'll go further back. I'll state that um, one thing that would be reasonable to try to understand first is what the local limit is in that case. And I suspect it'll converge to some alpha stable version of some random analytic function. And you could maybe even plausibly write down what that is. Um, but it's not totally obvious to me what the behavior of this should look like. I haven't done that calculation.
Thank you. Emmanuel?
Great talk. Thanks a lot. I have a couple of questions. So, in your main theorem, the psi j's are between minus one, are just minus one uniformly random polynomials, or can you do the same for like minus 1, 0, 1, or
Yeah,
other?
any mean zero and sub-Gaussian works. Our
Okay.
theorem is stated that way. And it probably also works for just mean zero and like a 300 moment being finite. Some big moment is good enough. Yeah.
Okay, cool. And my other question is about the so about MN. So I would like to understand what happens when MN is very small,
Hmm.
and maybe to get a upper bound of the probability that MN is very small. Do you have results in this direction?
I think we probably could get such results, but it depends on the scale. So, sort of what's going to happen if you ask beyond this scale is you're going to sort of quickly experience a trade-off between the number of non-smooth points and this small probability. So, for instance, if I were to ask for separation on the order of like n to the negative n, which is just like comically small, then that should probably only be witnessed by double roots,
Right.
right? And then you're really looking at some very specific algebraic property.
Right.
So I think that there are probably results we could prove depending on the scale of epsilon you care about.
So how about exponential scale? So it's a probability that Mn is less than e to the minus Cn. Could you show that this decays exponentially fast or something like that?
So I think it actually shouldn't, just because the probability of a double root at 1 is 1 over n squared. So if
Yeah,
you if you throw away these sorts of sillier examples,
yeah. Let's say away from the roots of unity or something like
yeah, so I guess the way I would think about it, it's maybe plausible. Something like that could be proven as an upper bound. And so what we have is we did this Gaussian comparison because we cared about the actual number. If I want an upper bound, you can get away with just much stronger Littlewood-Offord theorems. And there, maybe these Littlewood-Offord theorems by like Rudolphson inversion from random matrices are useful here because they go up to an exponential scale. But it depends on exactly the flavor of the statement you would want. So something that can be proven is you do have small ball bounds for sort of a typical z up to an exponential scale. Not necessarily the sharpest exponential scale. It's not totally clear you could get up to like 1/2 plus a low 1 to the n scale, but I think you could probably get exponentially small scale. So it might be possible with the right statement as an upper bound. A lower bound, I think, would be a lot harder.
Yeah, I mean, generally speaking, I'm interested in what happens even you fix a transcendental number, let's say Z,
Mhm.
and what's the probability that it becomes a root? So this
Yes.
should, I think, decays exponentially fast, and I think there are theorems like this, depending on how close the transcendental number is to the unit circle. But if you take it on this unit circle, um, yeah, I think I don't know how to prove that the probability that
Hmm.
this given number is a root decays exponentially fast. Um,
Okay, interesting. I think, okay, it's definitely less, what I'm about to say is less interesting. I think that it shouldn't be so bad to prove that it decays faster than a polynomial. Getting exponential, I think, is going to be a little
Yeah.
bit of work, but not necessarily impossible. It's something, I'll give it a little bit of a think and I can follow up with you.
Okay, cool. Thank you.
Yeah.
Any further questions from anyone?
Yes, can you hear me?
Yes.
Yes.
At the beginning, you talked about the number of real zeros. Do we
Yes.
also know something about their location on the real line, their distribution?
Yes. So they're going to be not too far away from one or and negative one, which behave sort of the same. And beyond that, we know what the sort of local limit is of the point process. So if I zoom in at a given point, let's say zoom in near one, they're typically spaced on the order of 1 over n away from there. And we know exactly what the limiting distribution is for this point process. So they're pretty clustered around 1 and negative 1, but there are going to be some roots that are macroscopically far.
Thank you.
Yeah.
Great. I think that's everyone. So I'm going to propose that we unmute and give Marcus a big round of applause.